Good morning, everyone. Thank you all so much for the opportunity to share a bit about the research that I'm interested in and excited about. I'm Cacey. I'm an assistant professor at Swarthmore College, and I lead the SWOT grains group at our college. So in our lab, we are interested in understanding more about creep and failure in granular systems. We use photoelastic imaging techniques as a way of getting all attainable information at all scales of a granular system as it creeps and fails. Using this information with the hope of ultimately determining a framework or model to help us better understand this behavior in granular systems. So, as we've learned extensively this week, granular material is quite fragile. It can readily shift from behaving like a stable solid to flowing like a liquid. We expect granular material to act like a solid when we're walking on it, but with just the right disturbance, we can make that material shift and start to flow and ooze like a liquid. So the video that I'm showing here is an example of this phenomenon in action. This is a video that I took while visiting the Agadones dunes several years ago. And in it, it shows that with just the disturbance of shearing the sand with my hand, I was able to make the sand transition and to start to flow like a liquid. So this is just one example that highlights how Earth's landscapes can exhibit this dual nature of granular media, readily shifting from behaving like a solid to flowing like a liquid. Sometimes it's a very beautiful looking phenomenon, like in the video here, but as we know, it can also be quite destructive. So understanding more about this transition and ultimately being able to predict failure in granular systems is an area of great interest. I took this video several years ago during my one and only experience doing field work. So I like to, I like to think of it as my brief stint as a geomorphologist. So maybe the career as a geomorphologist didn't quite stick. No fault to Doug Jermack, but it didn't quite stick. But it still helped to inspire what has become like a it still helped to inspire what has become a years-long effort for me and our group, trying to understand why granular materials shift from being like a solid to being like a liquid, and hoping that we can explain that transition. The approach that we use with our research is to use a multi-scale approach to understand granular systems. We want to learn how this flow at the system scale or macro scale of disordered materials depends on micro scale configurations or interactions. So doing such requires us understanding or an interplay of what happens at the scale of a single grain, such as local packing behavior, grain contacts, any single grain rearrangements, or void spaces to the grains, up to the intermediate scale of our system, clusters of rearrangements, intermittent flows, or the force network of our system, and hopefully connecting that information to help us understand the flow in a granular system, how these work to cause a system to creep and to ultimately fail. So that has led to us having a couple of overarching questions that motivate our research in the group. We want to use information at all scales of our granular system to bridge together maybe precursors or signatures to creep and failure in granular systems. Can we unite the motion of our granular system with the forces and geometry to learn what causes a granular system to fail? And then with this information, can we develop a sort of predictive framework or model that describes this behavior? And even ambitiously, can we control such flow responses or optimize such flow responses once we understand this behavior? So quite lofty questions, but I think this is the perfect place to share those ideas and thoughts because I can get some great insight from you all. So during the presentation, I'll share the progress that we've made in our experimental project to try to address these questions. And I'll also share some kind of open ideas and questions that we found along the way. So hopefully this will motivate some discussions and maybe even a few answers. So as a physicist does, we approach the problem by trying to find the simplest experimental system possible that can exhibit the physical laws of interest. So in my case, it's grains in a box. We have dry circular grains that we form into a simple configuration, and then we cause the granular system to start to flow or fail, and we observe different features about the system as a result. So here's an example, just like an illustration of the type of experimental system that we choose to study, where we have grains that are in a cone-shaped pile. And when this system is tilted above a yield stress, the granular system starts to flow, as shown by the image here, where it appears as though there's this abrupt kind of flow along the surface of our material, and then a kind of frozen, seemingly solid bulk. But with our experimental setup, we can do things like track the displacement of the individual grains, and we see that the transition is not as abrupt as it seems. It's far more complicated and non-uniform. So that's shown here in this image taken from our experimental data, where I now have a cone-shaped pile of granular media, and I'm coloring each of the grains according to the amount of displacement that the grain exhibited during the experimental run, during the failure event. So we see that the grains at the top are exhibiting that kind of rapid surface flow, but there's also significant granular motion deep within the pile. Also, as you've learned so far, we've referred to this type of behavior as a creeping motion, this sort of subyield deformation that's exhibited in granular systems. This is a robust feature that is observed in shear granular systems, and as we learned from on our previous talk and from past experimental work, creep can be observed even in the absence of such disturbances or shear. So it's a robust and interesting feature of granular systems. And lots of work has shown how the velocity of granular media during failure decays exponentially with depth. So it's been robustly shown in quite a few different systems. So that's what brings about our interest in learning more about it with our experimental work. So here's the experimental system that we use in our lab to try to understand more about creep and failure. In it, we have a pile of grains that we form to be just under a meter wide in an acrylic chamber. We form this by allowing grains to flow through a hopper that's at a fixed location above the surface of the acrylic chamber. So it's kind of like creating a pile using a localized source procedure, like so. And then the grains flow, and then they naturally kind of fall to a critical angle around the angle of repose of our granular media. Then we have an apparatus here, a mechanical arm that's connected to a stepper motor. This is used to instill disturbances onto our granular pile. So this stepper motor can rotate the mechanical arm at different rates in order to tap the pile periodically at set intervals of time, instilling a disturbance. The hope is that these disturbances on the pile can act to mimic the larger scale kind of geological activity that we observe in nature. So this is how we form our pile. The key here, though, is that we propose that the disturbances are just acting to accelerate creep. So we have seen before that that creep can occur in the absence of disturbances, and the act of disturbing our pile is meant to kind of accelerate that creep and failure event. So each of our experimental runs lasts only about a few hours. The key to the experiment is that the grains that we are using are made from a birefringent material. So when the material is stressed, it exhibits birefringence upon being stressed, and it alters the polarization of any transmitted light. So we view the experiment through cross polarizers so that we can make use of that feature. This is how we can get force information from our grains in addition to position information. So we record our experiment using two cameras that are simultaneously kind of taking images of our pile during the experimental run. One that's viewing through cross polarizers so that we can get force information, and the other that is viewing through without a polarizer, giving us images with unpolarized light that we can then use to track each of the grain's positions and learn more about the displacements in the granular system. So this is how we're able to track the grain scale information, force information. We can track the behavior of the entire system. We track the disturbances that we're imposing on the system. So we have all this attainable information about the experimental process as the granular pile creeps and ultimately fails. We also attach an accelerometer to the mechanical arm so that we can measure the rate at which the tapping is occurring and the forces of the tapping. So here are a couple of images that give you examples of what our experimental data looks like. So the images serve as our experimental data. As the creep and failure events are happening, we're taking pictures every 2 seconds. And here are 2 videos that I'll show. One is where I'm playing both where I'm playing back those images at 10 frames per second. So we run the experiment for about 2 to 3 hours, typically. So for any given experiment, we have thousands of images that we can work with to give us a time evolution of the creep and pile that's occurring in our granular piles. So first I'll play the top video and highlight a few things. So here I only took images that were kind of highlighting some creep and failure events that were happening in a typical experimental run. With these images, we're able to successfully track most of the grain's positions at each of those time steps. So we have information about the grain's displacements over the course of an experimental run. We observe different rearrangements that happen deep in the bulk of our granular system, as well as more substantial kind of intermittent surface flows that occur. And we're able to track the shape of the pile too as it changes. So we keep track of that information. We're also able to track the void spaces available to each of the grains. So I'll show you all how we analyze each bits of that information. And then I'm trying to play the bottom video. There you go. Okay. So while we're taking those top images with unpolarized light, we're simultaneously taking images using the camera with cross polarizers. So we're able to match the positions of each of the grains with the corresponding forces that they're experiencing. So we're able to see how the contact forces of our granular system have this heterogeneous network. We call those force chains. And we can observe the grains that are experiencing the strongest forces or constituents of those force chains in the granular system. So we can track the changes to the force network. Simultaneously, we're tracking the changes in positions as the grains creep and flow. So using these images, we're able to look for signatures or precursors to creep and failure at different scales of our system. So I'll talk you all through the information that we get at the grain scale, intermediate scale, and system scale that allows us to explore what ultimately causes creep and failure in granular systems. With the photoelastic imaging technique, it's really nice because we're able to pair kinematic information with dynamic information, as well as tracking geometric signatures that are present in our granular system. So I'll talk through what we observe at the system scale as we track the flow of our pile and the changing shape of the pile during this flow events. We'll talk a bit about the different force chains that we observe and the interesting kind of rearrangements that happen just before a major kind of failure event in our granular pile. And then we'll talk about what we observe at the particle scale, how we're able to track grain contact forces, as well as track the changing unoccupied volume of the granular system. So making connections to the micro scale rearrangements to the ultimate flow of the system. So first, with our system scale, as I mentioned, during the experimental run, we track the position of each of the grains at each time step. So that gives us information about how grains displace during the experimental run. So here's a run where we have a kind of substantial surface flow. I call it an avalanche events that occur during the experiment. Here I have each of the grains labeled by a color according to the displacement that the grain exhibited during an experimental run. We're able to successfully track most of the grains for a full experimental run, except for ones where maybe they're displaced a significant amount between each time step, so we can't track those. But most of the grains we can successfully track, so we get a good sense of how the system behaves as the pile is disturbed to creep and ultimately fail. As we're tracking these displacements, we simultaneously look at different features of the system, like the pile's angle, the angle that the pile makes with the surface. So that's what's plotted here as the pile's angle as a function of time over the course of an experimental run. The grains here are colored by their displacements, and as the displacements occur, we find that the pile kind of relaxes with each sort of creep or failure event to lower pile angles. Then we compare that for different experimental runs. For each of our experiments, the piles will creep due to those disturbances, but not necessarily have a failure event. By that I mean a kind of intermittent, significant surface flow avalanche that occurs. It varies from one experimental run to the other. So we form the pile by allowing grains to flow through our hopper to form the kind of ultimate pile at a critical angle. But there's a slight variation in that angle from one run to the next, right? No granular pile is exactly like the next. And we find that when granular piles happen to form initially at a steeper angle, they are more likely to exhibit an avalanche. That's what I'm showing here in our data. So I'm pairing side by side an example of an experimental run where there are more substantial avalanche events with an example of an experimental run that was prepared in the same way and ran for the same amount of time, experienced the same disturbances, but only had some sort of creep events that occurred during the experimental run. We measure the pile's angle as a function of time for each of those runs. And here I'm showing an average, the red being piles that avalanche during the course of an experimental run, and the black being those that just creep but didn't have these avalanche events. And typically when a pile was formed, happened to form at a higher initial angle, it was more inclined to fail. And those failure events would lead to the pile typically relaxing to an angle that was below that of creep. So while that was a pretty consistent feature that we observed in the behavior of our piles, we certainly don't understand more about it. So I'm hoping that during the time here in the program, I can understand a bit more about that. That's just one of the questions that I have. Why such a slight change in our pile angle, a slight change in one granular configuration of the pile to the next can lead to drastically different outcomes? How can we change the effect of our preparation to sort of set a certain angle? Like, as I mentioned, we form the pile by allowing grains to flow through a hopper, so flowing through a funnel to form the pile. If we prepare a pile in a different fashion, how would that affect the ultimate response that a granular system has? We use a set protocol of tapping the grains at a set time interval. But are there different ways that we can change the disturbance protocol in order to probe particular responses? Maybe tapping for a period and then allowing the system to relax and rest, and then see how that influences the behavior of a granular system. And then lastly, why those disturbances in some instances promote flow and failure but compact the grains in other instances. So there are a lot of kind of interesting questions that have come from our experimental observations so far that I hope that we'll get a chance to discuss together. Now let's move to another thing that we've done to understand a bit about the system's flow, and that was to try to change the base, to add texture to the base on which the pile is formed, and see how that influences the type of flow response that we get. So this schematic here kind of represents the idea that we used. We replaced a smooth base on which the pile was formed with bases that have different textures to them by using acrylic sheets and laser cutting different designs. We've tried two designs so far, a triangular base and a square base. And our goal here was to understand a bit how this base topography can influence the type of flow profiles that we observe. So here's an example of what we've observed so far. So we've tried two different basal shapes. So to compare with the smooth surface, we have a base that has square pillars and a base with triangular pillars. And here I'm showing color maps with the same scale of the type of flow behavior that was observed in each of those cases. And next to it are plots that show the fraction of grains that moved above a certain distance as a function of time. So we see that just by changing those changes to our base profiles, we see that our surface flows is substantially lessened. So this kind of hints to us that surface texturing can be a viable method for controlling the type of flow response or stability that we have of our pile. So this is something we want to explore a bit more as well. If determining if there are like optimal types of bases that we can use that will manipulate the flow profile, and then trying to understand more about what's being changed in the local packing structure of a granular system or its force network that's being influenced by this basal shape and leading to different responses. Next, I'd like to talk about what we observe at the intermediate scale here. So now we're trying to look at features like rearrangements of clusters of grains or the intermittent kind of flow behaviors that we observe to connect to what we observe at the system scale. So in this animation here, now I'm coloring the grains' positions according to how much they displace at a set interval of time. So blue are grains that did not move above a distance threshold, and then you'll see red grains are those that did move above a distance threshold during the experimental run. So not only do we see flows happening at the surface pretty occasionally, but we also see clusters of a few grains, sometimes even just single grains, that are rearranging within the bulk of the pile. We track this behavior by looking at the fraction of mobilized grains as a function of time. So these kind of peaks here are illustrating moments in which there are grain rearrangements that are occurring. And then we have a kind of substantial peak that occurs when there is an avalanche event during the experimental run. Now we compare that information, that kind of behavior of the motion of our particles, with some dynamic information. For that, we use our photoelastic images. So here we're able to track the contact forces using the images taken under polarized light, but there are quite sensitive changes that happen during the course of an experimental run. So to be able to highlight those kind of changes, we use a difference of our photoelastic images. So this is a great, initially kind of grayscale image here, but what is found by taking the image of the force network at the point of an avalanche and subtracting that from all of the images leading up to it, so that we get a sense of how much the force network has changed leading up to a failure event. So when we see white or black pixels, that's indicating changes to the force network that was observed over the course of the experimental run leading up to the failure event. And then we quantify this by identifying fractions of pixels that change over the course of the run. So here I'll show a plot of the fraction of changed pixels as a function of time, where it is 0 at the point of the avalanche, and it's greater than 0 when there is a distinct difference in the force network compared to that point. So we see there's a lot of changes that are happening in the force network, among the force chains, well before the avalanche actually occurs in our system. And then we can nicely map those two. So the great thing about the experimental technique that we've had is we compare what we've observed with the grain's motions with the changes in the force network. So this plot is an example that highlights that, where in red I'm showing changes to the force network as determined from the difference images, and black is showing the grain rearrangements that occur, which we found by tracking the positions of the grains. So we're able to nicely map the changes in the force network that are acting as a signature to an ultimate failure in a granular system. And of course, there are many more questions than answers here. So we want to know from here, how can we learn which grains within the pile are responsible for the ultimate flow? Can it be that there's a single grain or a cluster of grains within the force network that are shifting and they act as a catalyst for this ultimate failure event? It will be really interesting to kind of understand a bit more about that. We also want to know more about how the grain rearrangements before failure compare to those after failure, and what expectations we should have about the force chains or the force network as the system is giving way to fail. So last, I want to talk about what we observe at the particle scale. So by tracking the positions and the forces on each of the individual grains, we can do things like detect the strong context of a granular system and learn more about the void spaces that are available to each grain to have the potential to rearrange. So first, with the strong context, we use the positions that we get from the unpolarized light images with the force information from the polarized light images to find our strong contacts. By that I mean the contacts that are above an intensity threshold. Since we can't quite fully quantify the contact forces, we can just say if the contact was strong enough to be resolved in our image or if it is not. And we find when we look at different regions of a pile, there can be some changes to the force network without observable grain motion. So there are changes that are happening in one region of the force network that is influencing other regions of the pile. We also looked at the void space. So for this, I got help from Luke Davis, a theoretical physicist at the University of Edinburgh, who used a voxelizing technique to identify all the void spaces available to each of our grains. And this figure here is showing the void spaces labeled by color according to the sizes of the void space. Our hope being that we can connect the kind of available space to rearrange with the grain with determining whether or not it will ultimately fail. And our initial results do show that there can be a signature in the geometry that's exposed by looking at properties of the voids. So for example, we looked at the void unoccupied volume. This is like the void areas available to our system, and compared it to the fraction of grains that move during the experimental run. And we do observe a signature that coincides with substantial flow events that are happening within the pile. We also observe that when piles avalanche, there tends to be more void space available to grains compared to when piles creep. So there's kind of a densification that's happening for piles that creep only that makes it distinct from those that have failure events. Yeah, so, and then lastly, open questions in this area is we want to be able to ultimately link information about each grain's void space and the contact force that it's experiencing to the resulting rearrangement that the grain shows. And it would be great to be able to get initial positions of grains and its void spaces, knowing its force network, and then be able to say, will this pile have a failure event? How will this pile's creep behavior be exhibited? It would be great to ultimately make that connection between what's happening at the scale of the grain to the flow that we observe in our pile. Yeah, so in summary, we've been able to get quite a bit of information using our experimental technique so far, but there's still quite a way to go. We use our photoelastic imaging to have a substantial impact on this problem because we're able to look at position information and force information to learn more about the ways that granular piles creep and fail. So I wanted to make sure I left enough time to thank the people that are responsible for the work. Oh, I must have mistakenly deleted the. Oh no! Oh, that's surprising. Okay, I think I mistakenly deleted the slide. So I have to make sure if I do nothing else, I need to thank the people who actually did the work. So our college is an undergraduate institution, so the work was done by students who were doing undergraduate summer research projects, and obviously did an amazing job doing this work. And we recently incorporated Luke Davis, who has some experience looking at insertion space and void spaces in disordered systems, and has been really great asset to the project as well. Thank you all for your attention.
Yeah. We have time for a couple of questions. Yes, this figure.
Ezequiel Ferrero here. Thanks. Very nice experiments and talk. In fact, I can use this slide to ask. So this sample-to-sample fluctuation or changes of what you will call the critical angle, no? So this also happened in disordered elastic systems. But a question I want to ask about this is, when you increase the system size, does this fluctuation shrinks and you have a more well-defined critical angle, or it's not the case? Yes.
So the question is if I increase the
yes. So this sample-to-sample fluctuations of the critical value exist in this disordered system as well. But when you increase the system size, this fluctuation is smaller and smaller. So you can define precisely a critical angle in an infinite system eventually. I don't know, it's a question.
Yeah, I suppose that will be able to apply for our system as well. We haven't tried different system sizes like larger piles. The way that we determined the angle of repose for this system was to allow a pile to form kind of a cone-shaped pile and measure the angle of repose from there. But as you pointed out, there's obviously a lot of variation from one experimental run to another. So we will have to try maybe having a larger system size too.
It will be interesting to see if there is a system size scaling of this. And the second question is, you have there the avalanches, no? The number of particles that move in these little spikes. Do you have enough statistics to do a distribution of these events? I mean, say
I
to plot the
definitely.
histogram of the sizes.
Yeah, I definitely could. I haven't done that yet, but we have many experimental runs where I can track the flow events that are happening and see if there is some kind of interesting trend there. But we haven't tried that out yet. That's a great idea.
Okay.
Yeah.
Thanks.
Thank you.
Yes, Itai.
Hi, Casey.
Hi.
Itaina from Sydney University. Very interesting work. There's access here to 2 points of information that you study, which I liked, is the deformation, the motion of the grain, but also the stresses. And I was wondering if, one doesn't mean the other when there is movement. So I can imagine fixed grain where the stresses are rotating and maybe there's not prominent on observable motion of grains. And I can imagine grains that are moving, of course, it will also affect the stresses. And I was wondering if you've seen maybe the stress rotation as a precursor to those events of motion. Yeah.
Yes. So that's what we think is happening, that there are some, based on what we've observed from looking at the difference images and tracking the change in the force network, that there are some pretty substantial changes that are happening in the force network before that failure event. Okay. So I think I just need to kind of think my way through how to really
you need a correlation.
To how to really show the correlation there, right? But that seems to be the case. I think you're going in the right direction. That's a good point. Thank you so much.
Hi, David Meir, Emory University. Wonderful talk as usual. I'm wondering a lot about changing the floor. To what extent do you think the reduction in avalanches is due to the effect the floor has on the protocol of the packing versus if you could, pack it, teleport some particles out, put the bed in place, how would those two things be different? I guess where I'm going to with this is how similar is changing the bed geometry to just pinning particles in place. And that doesn't have to be just on the bed. It could be on the floor. It could be anywhere.
Yeah. I think that's a really cool idea that you have there. I think you have a good point that this is just at the beginning stages, so it's certainly something we need to play around with a bit. But it does seem as though when we have those pillars in place, there is a bit more organization among the grains that's happening, like grains of the same size. I think I forgot to mention it was a biodispersed arrangement of grains. But we kind of get an order configuration of grains within the kind of bottom region in between the pillars and things. And so you're right, that may be kind of influencing the flow profile quite a lot. For the comparison, we tried to only compare runs that had the same initial angle and we used the same disturbance profile. But there are, as you point out, aspects like that we still need to kind of understand a bit more. And even, like you point out, play around with changing the surface profile, maybe even slight changes to the base profile can have an interesting impact, and we haven't explored that yet. So thank you so much.
Yes,
Hi, Casey. Justin Burton, Emory University. Looking at the first graph there, there's some red lines that start up high at a high angle, but there's also some that even start below some of the others that creep, right?
Yeah.
So I was just curious, you kind of answered, I guess, some of it with the looking at the volume, but have you maybe taken some of these and said, well, maybe this one starts at a slightly smaller volume, just kind of integrated over the entire area that the particles take up, and this one's more well packed, and that's why it
Yeah,
creeps instead of avalanche.
I think you make a good point that there's a connection to be made between the void spaces, which is probably more informative compared to the surface angle. And we've tried to do that a bit to look at what's the distribution of actual void sizes available to grains as opposed to just the surface angle. And there seems to be a bit of a correlation there. So you're right that there might be a more like promising avenue to explore.
The critical angle of repose probably depends on the packing fraction. Sure.
Yeah, it depends on the packing fraction. With these grains, we periodically put powder on the grains and things. So there are things that they're changing probably the friction or the way that they pack from one run to the next. So yeah, there are a lot of factors in here that make it pretty complicated. Thank you.
Okay.
Hi, Duncan here at University of Cambridge. Your beautiful field experiment at the beginning.
Yes.
So there's a lot of interesting things going on there, but you're basically making a disturbance at the bottom of a pile,
Yeah.
which then is this kind of backwards propagating wave all the way up. Have you tried doing that in the lab? And that's a kind of different forcing from what you're doing, right? You're tapping the thing, but if you actually scoop out a little bit at the bottom, you'll see interesting.
Yeah, that's a good point. I haven't yet figured out how to do that experimentally, but I've thought about doing that. Just in general, changing the way that we're disturbing the pile to have, like you point out, more like localized disturbance, maybe vibrating at a particular position and things. So we want to try that out. I haven't yet, but I want to try that out.
Like you just take some of the grains out.
Oh, take the
Like
grains out.
having a gate on one side and just opening it. And
Oh yeah. Oh yeah, that will work too. Thank you.
Sandesh.
Hi, thank you for your talk. I really like the beautiful images that you have. I had a question about the video you showed about in the creep case where you had these little red particles show up that were moving above a certain threshold. And I was wondering, the size of those red clusters seem completely random to me.
Yeah.
But I was wondering if across multiple experiments there are some correlated lengths in this system that lead to creep, and above a certain correlated length, you're 100% sure that's an avalanche. Have you seen anything like that over there?
Yeah, so, okay, I think that's a great point, too. And I got to another question that someone mentioned about doing histograms. So I do need to look at histograms and compare them for creeping piles to avalanching piles to see if there's a trend there. So far, we do see the kind of trend that we see is an increase in the kind of creep events that occur just before an avalanche happens. But there isn't much more of a trend there. Like the point at which an avalanche happens seems to vary a bit from one experiment to the next. And there are some features about the pile, like as someone else pointed out, the packing of the pile that informs if it will creep or fail, but not so much about when rearrangements happen that determine if it creeps or fails. But I think I'll explore other ways of looking at the data to see if there actually is a signature there that we just haven't teased out yet.
Yeah, because I wonder if you were talking about looking at the empty spaces in the pile, and I wonder if those length scales correlate to those creep length scales.
Yeah.
That would be interesting. Anyways, thank you.
Thank you.
So, hey, I'm Viet from Sydney University. So I'm curious about your experimental setup, since the grain will be at least at the top of the hopper,
Yes.
so it will drop down. So do you control the height of the hopper, that's the drop distance? So it have the effect to the initial stress state of the whole system. So do you consider about that?
Yes, yeah, that's a great question. We do. We have the hopper at a fixed point that is installed onto the acrylic chamber, so that's at a fixed point above the surface of the acrylic chamber, and follow the same extent for every experimental run. And you're right that influences the packing of the pile and the type of stress profile that the pile has at the start of an experimental run. That will vary from one run to the next, but we do kind of consistently prepare it the same way. Yeah. Thank you.
Eric Weeks, Emory University. I like that you're thinking about the base. And even in the flat case, I was thinking that like the depth of the base below the pile is different from the tail end to the top. Mm-hmm. Does that matter at all? Like you have forcings that extend all the way down, even at the very deep side. But do you see any differences in behavior between like the very deep side of the experiment and the very shallow side of the experiment?
Yeah, we do see some We do see a bit of behavior like there. It does seem that the flow, it seems to kind of be more concentrated to one end of the pile when we have those changes to the basal profile. So I do want to do things like changing like the height of the pillars and the arrangements there to see if we can understand a bit more about that behavior.
But my question is even about like the flat base.
Yeah.
Like even in the flat base case, do you see a difference between the left side where it's shallow and the right side where it's deep?
I think so. Even then, it's less likely for there to be kind of rearrangements events at the area where it's deep, or I should say rearrangements events that are observable with our experiment. We do kind of observe some differences there, but it's definitely interesting that there's something happening even in that region in the bulk, that something happening with the force network that is causing a rapid flow behavior somewhere else in the pile.
Cool.
And so there is still a connection there.
Okay,
Yeah.
thanks.
Thank you.
Thanks. Super cool talk. Very interesting. Thanks, Casey. My question is not dissimilar from Eric's.
Okay.
And are we supposed to introduce ourselves? I'm sorry. Kimberly Hill, University of Minnesota. The question is partly about. So I'm going to be very specific. When you showed the failures for the differently shaped bottoms, it looked like for the triangular one, there was sort of a peak in failures, maybe near where the peak was. And I don't know if you can scroll back to that.
Course.
But I'm sort of similarly, is there correlation with some numerical, quantitative distance from the disturbance of the base to the top?
Here we go.
Yeah. So there's kind of a couple little peaks of where the disturbance is for the triangles, and just wondering if you've done studies yet, or you intend to look at those correlations where you get more avalanches relative to the triangle. And then, of course, the question is really interesting about, whether it's related to force chains or local packing.
Yes. Yeah, I think those are both good points. Even with this sample image I showed here, I think I have a backup slide with this. Okay, yeah. So this is probably better. Yeah. So even with this, you can kind of see how you get this more like crystalline regions here when there are pillars available. So you're right. There's something there's some influence here with the packing that's happening, and there are points where force chains are kind of emanating from those pillars too. So there are some changes that are happening in both the local packing and the force network that we need to unpack there.
Very nice. And nice pun.
Oh, yeah. That was totally, that was intentional. No, actually, it wasn't at all.
Okay. This is a break, so we can take all the questions to the courtyard. I'm sorry about that. Let's thank Cacey once again. Yeah, we'll be back here in 30 minutes for Paulo and Karen's talk.
Moment to thank the students. I mistakenly deleted the slide. And so this is everyone who did the work. Thanks, everyone.